Intermediate Algebra for Statistics, using substitution to solve systems. Lesson objective: use substitution to solve systems of linear equations. Recall, solve by graphing. Find the solution to the system of equations by graphing. So we have our system, which is two linear equations, x plus y equals 20 and 1/5 x plus 1/2 y equals 8. One way of solving by graphing is to put all the equations into y equals mx plus b form and graph. So we have the first equation, x plus y equals 20. Solving for y, we subtract x to both sides, and we're left with y equals 20 minus x, or we can say that's the same thing as y equals negative x plus 20. They're equivalent. For the second equation, the first step I'm going to do is to clear the fractions. So we need to multiply every single term of the equation by the least common multiple between 2 and 5, which turns out to be 10. So we have 10 times 1/5 x, 10 times 1/2 y, and 10 times 8. 10 times 1/5 is 2. 10 times 1/2 is 5, and 10 times 8 is 80. So we have 2x plus 5y equals 80. Solving for y, we subtract 2x to both sides. The next step, to isolate the y, we need to get rid of the 5. So since it's multiplying, we do the opposite and divide. Now we have to remember that the 5 is dividing both terms on the right hand side. So we're left with y equals negative 2/5 x plus 80 divided by 5, which is 16. So we have both equations in y equals mx plus b form. We could use graph paper, or we can use our graphing calculator. Using the graphing calculator, we hit our y equals button, type in the first equation, negative x plus 20, type in the second equation in y2, negative 2/5 times x plus 16. Next, we want to position the window setting so we can see the intersection. So to get an idea what window setting we need, I'm going to use the table feature. So I hit second and graph, which is table, and I'm looking for the x where y1 and y2 are the same. So as we see, around 6 to 7, these values are very close. So the range for the x's need to be centered around 6 or 7. As far as the y value, the y-intercept is 20, and it appears that they're intersecting around 13 something. So for the window settings, when you press the window button, the x setting that I'm going to use is negative 1 because I want to see the y-axis, and then my x max is 12. And the reason why I picked 12 is because the x-coordinate at the point of intersection was about 6. So if I go from negative 1 to 12, 6 or 7 is about in the middle. I want to count by 1s on the x scale. For my y minimum, I'm going to use negative 1 because I want to see the x-axis. And then the y max is 20. And the reason why I use 20 is because that is the intercept for the first equation and the intercept for the second equation, 16. So in this window setting, I can see both y-intercepts for both equations. So using this window setting, if I press graph, I see that this is the graph where the intersection is about here. And if we hit second trace, which is the calculate feature, I go down to number 5, which is intersect. Choose the two equations and hit a guess, and the calculator is telling me the intersection is about 6.67 and the y value is about 13.33. And if I want to verify this by using the table, I hit second window, which is table set. I want the table to start at about 6.6, and I want the table to count by 0.01, and we can see at about 0.6.67 the y values are very, very close, 13.33. So using graph paper, the graphs would look like this, and zooming in, we would see that the intersection point is not at a corner of the box. So this is an approximation. And the solution does turn out to be 6 2/3 and 13 1/3, but we can't get that from the graph. We can just approximate. So the last example shows a limitation to the graphing method. It sometimes produces only an estimate of the solution. We will learn another way to solve a system of linear equations called the substitution method that will produce exact answers for the solution. So instead of solving it graphically, we're going to solve it what's called algebraically. Less objective. Example 1. Solve the systems y equals x minus 1 and 3x plus 2y equals 13. Solution. From equation 1, we know that y is equal to the expression x minus 1. So what we could do is take the second equation, and everywhere we see a y, we replace it with the expression x minus 1. Now doing this gives us an equation where the variable is only an x. Once we replace x minus 1 for y, we have an equation that has nothing but x's, and we can solve for that variable using that equation. So solving this equation, we first do the distributive property. So we're going to get 2x minus 2. Next, we combine like terms. So 3x plus 2x is 5x. So we're left with 5x minus 2 equals 13. To isolate the x, we add 2 to both sides, and we're left with 5x equals 15. And dividing by 5, we see that x is equal to 3. So this means the x coordinate is 3. If we substitute 3 in for x in either equation, we can find y. So using equation 1, or we could use equation 2, but for this example I'm using equation 1. Everywhere I see an x, I'm going to substitute 3. So we now have y equals 3 minus 1, and of course that is 2. So the solution to this system is 3, 2. To verify the solution, using the first equation, we know that x is 3 and y is 2. The left-hand side should equal the right-hand side, so we're left with 2 equals 3 minus 1, and we have 2 equals 2, and of course that's a true statement. We have to check the other equation, so we have 3x plus 2y equals 13. Substituting x and y, we have 3 times 3 plus 2 times 2 on the left-hand side, and on the right-hand side we have 13. So applying the order of operation to the left-hand side, we have 9 plus 4, which is 13. So we have 13 equals 13. That's a true statement. We have verified that 3, 2 is on both graphs, and 3, 2 makes both equations true. We could also check the solution graphically. We graph both equations. We check that 3, 2 is the intersection point of the two lines. So we have to solve for y first for equation 2. Then we use our y equals button on our graphing calculator. We type in x minus 1 for the first equation, and negative 3 divided by 2 times x plus 13 over 2 for the second equation. And using our intersection feature, we see the calculator verifies the point of intersection is 3, 2. Using substitution to solve a linear system. Process. To use substitution to solve for a system of two linear equations. Number 1, we isolate a variable on one side of either equation. Number 2, we substitute the expression for the variable found in step 1 into the other equation. Now this is important. It needs to be in the other equation than the equation that we used in step 1. Number 3, we solve the equation in one variable found in step 2. So this will be an equation that will have only x's or only y's. So when we have one equation with only one variable, we can solve it. Number 4, we substitute the solution found in step 3 into one of the original equations and solve for the other variable. Thanks for watching.